Okay, so what I'm doing here is I'm going to be showing the solutions for that practice exercise I just linked on D2L, which is or I posted on D2L. It's series and parallel, just the same idea as the inductor, only with capacitor. And so if we look at the tables, what I'm going to be doing is looking at this first example right here and demonstrating that in multisim and the voltages and currents and phase angle. And then I'll be doing the same thing with the parallel example that you see here, demonstrating in multisim and showing the calculations and everything on it. So that's my plan, and I'm going to start with the series 10 ohm 330 microfarad connection here. If I look at this as being my schematic for my series example, the first thing I would do is approach this in terms of the total impedance. So when it comes to Z total can be determined as a rectangular value of 10 ohms plus minus J, and we have to do a calculation of the XC value here, where we have XC equal to 1 over 2 pi FC. So if I go through and take a look at that, I'm just going to look at my calculations that I determined here, and I came up with a value of 8.04 ohms. So if that's my minus J component to my impedance, so I would put 8.04 ohms in here. Okay, so I can convert that directly to its polar value. And if I do that as a polar value, that would be 12.83 ohms at an angle of minus 39 degrees. Now, what does that look like as an impedance triangle then? Remember, because it's a series circuit, we can determine the total impedance by adding them up, and that can be shown in a triangle. So we would have R equal to 10 ohms. We would have a minus J component here, a minus J component of XC, and it would equal 8.04 ohms. Now I know that isn't to scale. Maybe I'll just extend this a bit to make it look a little bit more to scale. And this is going to be my Z total value. Now, angle of impedance in the triangle is saying this is 39 degrees, and our Z total value is indicating 12.83 ohms. Well, we know that our voltage triangle is going to be looking exactly the same as an impedance triangle from a series circuit, because each one of these quantities is just multiplied by our total current in order to get a voltage. So what we can do is we can calculate our total current by dividing our Z total into our E source. Now remember, for this example, our E source was 120 volts, 60 hertz. So if I look at wanting to determine I total here, I can say I total is equal to E source at 0 degrees divided by Z total at angle 39 degrees here. So that would be 120 volts at 0 degrees divided by 12.83 ohms at minus 39 degrees. So back again, I forgot to mic up properly, so hopefully the audio wasn't too bad up until now. So now we're looking at determining I total. So we're doing a division of our E source divided by Z total, and the result is going to be a value of 9 9.35 amps as a magnitude, of which we know is the current's going to be leading the applied voltage now by 39 degrees. And that, of course, is supported by our ICE relationship, where we know the current is going to lead the voltage. If you pick voltage as the reference, current is going to lead. Okay, so that's what we see for our current. Now let's just calculate our the values in our voltage triangle. So we we have 10 ohms and 8.04 ohms of XC. So we'll just put the impedance triangle back here again, so there's no confusion. 10 ohms, 8.04 ohms for XC as a minus J component, and then we had 12.83 ohms here and 39 degrees for our angle of impedance. All we need to do is multiply each one of these quantities by our I total value in order to determine their voltages, right? So for VR then, VR is going to equal 10 ohms multiplied by our I total value. Our I total value was 9.35 amps, right? So we've got 93.5 volts for VR. Now what we need to do is figure out our VC value. What's VC going to be? VC is going to be the value of XC times I total. So don't forget XC times I total. So that's going to be 8.04 ohms times 9.35 amps to give you 8.04 times 9.35 to give you 75, let's say 75.2 volts. So 75.2 volts. So VC equals 75.2 volts. Now this, proving Kirchhoff's voltage law, this should be ES equals 120 volts, and this angle here should be 39 degrees. So if we just take a moment to look at the voltage current relationship here, remember in this circuit, I total equals IR equals IC. So they're all the same current, all in the same phase. And that current lines up with one of these voltages. And that voltage is VR. The current and the voltage of a resistor is always in phase. So that means we could say that I total is right here equal to IR equal to IC. And because of that, if we look at our applied voltage as the reference now, so we start from the reference, we can see we have a leading current here, leading I. And once again, we always go back to our acronyms to make sure that's supported by what we're finding in our results. So sure enough, here we have current leading the applied voltage, as it should for a capacitive circuit. And it's leading by 39 degrees. Okay, so there's our voltage triangle. We've got our current magnitude, and we should be able to go to multisim now and prove that all by. Okay, so here we are in multisim. So you see I have a series circuit made up of the 10 ohm resistance and the 330 microfarad cap, and connected to a 120 volt RMS 60 hertz source, and I have an ammeter to measure the total current. So the total current is what we had is 9.35 amps coming up here as XMM1 value. XMM2 is my VR value, and XMM3 is my VC value. And if you look at the two values and adding them up directly, you can obviously see that those two voltage values don't equal 120 volts if they're added directly. And of course that's because you need to add them at their appropriate angles. So 93.53 volts at 0 degrees plus 75.2 volts at a minus 90 degrees in order to come up with our to prove our Kirchhoff's voltage law. And if you do, you would find that equals 120 volts. So that's proving Kirchhoff's voltage law for this arrangement, and our total impedance is what allowed us to calculate this magnitude of current, AC current. So I'm going to now set up the oscilloscope in order to show you the circuit phase angle here. So I'm just going to do that. Okay, so here I've got multisim up, and I've got the oscilloscope connected. The oscilloscope's connected in order to measure the time delay difference between what you can see is for the channel A, the source voltage, and for channel B is the resistor voltage. Now, I've checked the resistor voltage simply because in a series circuit, if we have a resistor, we can use the voltage across it to represent the current in the circuit. One of our statements is always that voltage and current will be in phase for a resistive component. It doesn't matter whether it's connected in series or in parallel or part of an RC circuit or an RL circuit. It's a rule that always applies. So because of that, then the voltage across it being measured by channel B here is representing the phase of the sinusoidal current flowing in this circuit. So I'm able to do that. Now, when you look at the results on the oscilloscope here, notice how I've got the two time markers to compare the phase of the red sine wave to the blue sine wave. Now, the blue is the voltage of the source, and the red is the voltage of the resistor, of which we know is in phase with total current. So this is going to allow us to determine the circuit phase angle. And notice how we clearly have a leading current. So the red sine wave is leading the blue sine wave, as it should be for a capacitive circuit. And the total time displacement here is 1.8 milliseconds. So if you look at the screen to the right, you'll see the calculation I did, and we find out that we do have the calculated circuit phase angle of 39 degrees.